Let's get a little deeper. But you get these ideas, hopefully, as I say, you've got at least a visualization that will make it less abstract. And these ideas are abstract, so they are a bit of a challenge. But once we get that straight, then you're going to spend plenty of time doing problems, doing the mathematics. But keep this in mind. A lot of good questions come up. So as you study this, make sure you go ahead and ask them. And maybe you ask the same question 10 times until it clicks. That's fine. Just keep thinking, and you will. So our next sequence that I want to go into, and this is mostly conceptual, a little bit of math, but just to get you ready for that math. I want to talk about, we're going to talk about electrostatics first off. And so first, what is it not to be electrostatic? We'll talk about electric current just briefly, some interesting things. Then second, the interaction analysis, the analysis of electrical interactions between objects or particles, bits. And we're going to preview two main approaches that we're going to take. Fields and forces, that connection and those distinctions, rather abstract, and potential, electric potential, and potential energy. Then, so I'll do a little overview of those, compare and contrast those just briefly. And then we'll get a little bit more into the details of field and force, electric field and electric force, and electric potential versus electric potential energy, and how those are connected, and allow us to analyze and do some quantitative analysis of how things interact. So that's the plan. Let's start with electrostatics and not electrostatics. So first, electrostatics, this will be short, but let's get this straight, means that things are not moving around. Maybe they have moved, but not now or in the picture. And I'll write myself a little note here. Okay. So recall that we talked about transferring electrons, usually, right? Usually transferring. So remember the fur rubber. Fur ends in R, rubber starts with an R, so the electrons go from the fur to the rubber. Maybe the fur is lamb's wool or human fur, hair, going to some rubber or plastics of some sorts. So then the electron goes here. Remember that one, fur to rubber, and generalize that. Also, glass ends in an S, and silk starts with an S. So you go from glass to silk, the electrons go. So these guys, when I rub this combination, the electrons go here. This becomes negative because they actually got some extra little bits, and these lost bits, and they became positive. This will lose bits and become positive, glass or even this acrylic. To silk, this will become negative, and it got some extra bits, which gave it a little more mass, but not significant. Okay, cool. These are called insulators versus conductors. These are conducting materials like metals. So let's make a little quick distinction here, not a big deal, and see if that's clear. So when I say electrostatics, then somehow I have charged these, which is to say, often I've transferred electrons from one thing to another. If I have an insulating material and I make something positive, then I've got to take the electrons away, right? And so remember this, that when I take the electrons away on an insulating material, I have a region of positive, again, not protons, and not charges. There aren't anything really, charges don't exist. They are things, they're a lack of electrons that I've taken here. With an insulating material, that region of a net positive charge will stay right there. So electrons are not free to move in an insulating material. And it doesn't matter where I rub it. It doesn't have to be a sphere, but we're going to talk about the importance of starting with spheres. So if I rub it in some area, say over here, then that region will stay positive. Okay? Okay. So actually, I want to do that. Sorry. It doesn't matter, but we think of positive terminals as red, and some positive there. If I contrast that with conductors, if I take electrons away from conductors, there's still a lot of electrons there. And so that lack of electrons, if I take electrons off of here, then I get a region here that lacks electrons, but there's some electrons that will go, hey, I don't like my fellow electrons anyway, we're not very friendly, so I got them too bunched up, they'll spread out. And so the net lack of electrons will spread out, and so you'll have a distribution that's fairly even throughout this conducting material because electrons have moved. You rubbed it one place, but you've taken somehow electrons off, but the electrons have moved around, so it's not a one region of positive or lack of electrons. It's distributed throughout. And it gets tricky when when things are not spherical because you actually have buildup of charge around points. So it distributes in interesting ways, and we're not getting into that right now. But just so you know that the electrons inside a conductor will move around until they're settled in, and everybody's going, okay, I'm as far away from my electrons as possible because electrons don't like electrons, right? What happens when you put electrons on? Well, it's the same kind of idea. If you put electrons onto a conductor, you get a region of extra electrons. And that's what that negative means, right? And it'll just stay there in an insulating material, like silk, glass, or fur, or rubber, or whatever you do that with. Wood is an insulating material, right? If I put electrons on there, they're just going to hang out there because they don't easily move within that atomic structure, right? And it doesn't matter the shape, whatever I put those extra electrons, they're going to hang out there. Whereas on a conducting material, if I put extra electrons on here and they go like that, and they go, hey, electrons hate electrons, so they're going to spread out, get as far away from each other. Now there's other electrons too, so they spread out. Okay? And how exactly they spread out? Again, we're layering in the details. So interesting questions, but the distribution, or the excess electrons will distribute themselves so as to move around. And again, it gets tricky when it's a non-spherical shape, so we'll do a lot of startup with spherical shapes, however they go. And you get a lot of buildup on pointy edges too. Interesting thing. Okay, so that's what we mean by electrostatics. They may distribute themselves, but then they're settled. Now, I do want to make this point. You often see problems in textbooks that look something like this. They look like some object here which has some negative electric charge. Remember that? We did that last one. Let's say negative 3e, where e is the fundamental unit of charge. Or I could use coulombs, but 3 coulombs is a huge charge. That would be crazy. I could use microcoulombs. Micro is 10 to the negative 6, so that might be more reasonable, certainly. I'll use e. And I could put some other negative 2e here, and I could put a positive 7e. Could I put positive 7.5e? Could I do that? Remember the fundamental unit, E, is quantized. That is, aside from quarks, we don't have half an E. Right? And quarks are a funny thing. So I can say 7.5 times 10, can't I? Because that's 75. It's still in integer amounts. So you may see that and just realize that. Okay. So I might have a situation like this in a problem in my homework, and I want to know what's the total force on this guy. Well, okay, it's going to be pushed away by this one, because they don't like each other, they're the same. And it's going to be attracted here. But when we do those problems, we're treating it as electrostatic, even though if they're free to move, they will move. So that can be confusing if you have questions, ask them. They're good questions. If something's bothered you, try to dig into that and come up with a question. And don't feel silly because it took people hundreds of years to sort this out. Right? So we're treating it as electrostatic. If these were allowed to start moving, you'd start getting into differential equations really fast because the force strengths would be changing and the paths would be pretty hard. So you can think of them as stuck, or you can think of them stuck within an insulator or something like that. Okay? So that's electrostatic. We're building, right? So it's basic and not very useful, this sort of situation so much. But okay, what do I mean by not static? So let's go over here. So let's move over to this board. And we see we have conducting wires, right? So we got wires. And it wouldn't, be very good to try to run electricity through a stick of wood, right? But if we use a conducting material, usually copper, something like that, then we can have a situation where it's not static. There's something interesting that happens with this when we talk about a wire, right? Talk about a wire, and I've got an insulating material around it, and then I've got a conducting material running through it. Now, is that so I don't get shocked? Well, so it's kind of funny. What we have often are electrons that are free to move. Remember how many free electrons per metal atom? 1 to 4, yeah. So a lot of electrons that are bound in there, but it's those outer ones that can move around. So if this electron's going down, and this electron's going down there, right? And perhaps I should, well, I'll get to it again. They don't really flow like this, down like a water through a pipe. It doesn't work like that. They actually bounce around. They go back and they go like this. And so on. We'll talk more about that. But electrons will move through that wire. Now, is that wire electrically charged? Generally not, because if one electron comes in, one electron goes out. Well, we're not talking one. If 1,000,000 electrons come in, 1,000,000 go out. If 1,000,000,000 electrons come in, 1,000,000,000 come out. It's only 10 to the 9. So the wire itself is not electrically charged, but you do have some motion of stuff. Now, we'll get into this later, but I just want to say that we call this electric current, but it again is the electrons usually that are moving. That means that because Ben Franklin's piles, he called the negative pile is the one that it turns out that's where the electron goes. Could have been the other, could have been called positive. But with our math, it's easier to keep track of the flow of positive, which there isn't, right? But what we do is we call this electric current. We use the letter I, or lowercase I when it's an alternating current. Often you'll see that notation. Don't worry about it. And I think of it as why I guess you run out of letters, but also it's imaginary. There's nothing flowing this way. But the electrons are going the opposite way. But again, it's easier math. So when it's not static, we're going to deal with electric current. We're going to deal with how electric current makes magnetic fields and fields magnetic fields, all kinds of crazy stuff. Cool stuff. This is an introduction. Just let it go. I do want to mention that we have beams, so we can have beams of protons. It's pretty easy with hydrogen. It's just a proton and an electron. Separate them, get a beam of protons, and you can have a beam of protons. So I could represent it this way, or I could just as well, in this case, represent it as a whole beam. Somehow, clever engineers and scientists, physicists have figured out how to get a beam of protons going that way. And in that case, I'd say the electric current is going that way. You could also have a beam of ions. So whatever, take a bunch of carbon atoms, and how do you make it positive? Take the electrons away. So you've got a bunch of positive carbons, right? Positive carbon atoms flowing this way. And again, I is that way. So If you have a gas of ions, then we talk about plasmas and all kinds of cool stuff. Just laying the foundation, don't overwhelm. A beam of electrons, can I get that? Sure, you get a beam of electrons. So that's kind of a different thing than this. And when you have a beam of electrons, they're heading down one way, let's send a beam of electrons that way. And what direction is the electric current? The other. The actual motion is this way, but what we call the electric current is that way. And again, we're going to hit this a lot, so just, you're fine. And a beam of negative ions, that's atoms that have extra electrons. Sure, you can do that too. And yet if they're moving to the right, then the current's to the left. If they're moving to the left, the current's to the right. You'll see plenty of it. It's not a big deal, but it is kind of weird. And you might say, well, can't we just call electrons positive and then they flow in the direction of the... Yeah, you'd have to change a lot of things. And when you get used to it, it's not worth it. Okay, so we're going to do things. How do you make the electric current happen? We'll talk about that with force, or we'll talk about that more simply with energy. And so you hook it up to a battery, basically. That's pretty, no one needs to know that. An electrician doesn't often know all this theoretical stuff, but they can get the job done, right, up to code and stuff like that. So you hook it up to a battery and you run electrons. When you hook it up this way, we call this positive, and we call this the negative terminal. And we say that the, oops, hello, wrong color. The electric current is going that way, but really the electrons are going the other way. Nice and simple. We'll just start us off for this course. And they're not flowing straight on through. They're bouncing around like this. They're really only making about a millimeter a second progress. We call that the drift velocity. Again, later introduction, right? And we draw these nice pictures, but really our wires are all wacky and they're all over the place and they're all over the table and they're getting disconnected and all kinds of stuff. So that's the difference. We will talk about all kinds of cool stuff and uses for electric current, measured in amps or amperes. How we get electric current, various ways. When you do have that electric current, it can flow through, and just like rubbing your hands, it can create you can warm your hands by rubbing it. You can warm a light bulb, you can make it glow, you can do various things with it. There is energy associated with it. But it is interesting that the wire itself is not electrically charged. We talked about charge separation. Charge separation, we're going back over here and starting out with electrostatics. We're going to layer in these ideas, and we are going to try to be careful whether or not we're talking about conductors or insulators. Just keep that in mind, and we'll build our way up in complexity. So I think that's good, and let's talk a little bit more now about the two ways we can talk about electric interactions between objects.